So in this video of chapter number 9, okay, areas of parallelograms and triangles, we are going to see one more interesting proof that is related to parallelograms and triangles. So let's read what the statement is. Area of a triangle on the same base and between the same parallel lines is half. So let's highlight this. It's half. Okay. The area of parallelogram. Okay, so what does the statement read? What does the statement mean? We'll try to visualize. So first of all, let's draw two parallel lines. So this is my parallel line number 1. This is my parallel line number 2. So these are my parallel lines. Okay. Now, what they're saying is area of a triangle. So let me draw a triangle here. So this, let's say this is my triangle. Okay. So this is my triangle between two parallel lines. Okay, what is, let's give name to the triangle. So let's say this is A, B, oops, so A, B and C. Okay, now the statement reads area of the triangle on the same base. Okay, so this is my base, this is my base AB, and between same parallel lines, so these are my two same parallel lines, will be half the area of parallelogram. So the parallelogram that we are going to construct now uh, should have the same base, so same base AB, and it should be between the same two parallel lines. Okay, if that is what is the case, then the area of triangle will be half the area of the parallelogram. This is what the statement says. Okay. So now let us construct a parallelogram with the same base. Okay, same base AB, and between these two parallel lines. So this is how I'm going to make it look. Okay, so we can extend this. First of all, let's erase this. Okay, and we can extend this parallel line further. Oh, sorry. So okay, yeah, so we have these two same parallel lines. Okay, and this was my triangle ABC, and I've constructed another parallelogram with the same base AB and between these same two parallel lines. Let's name these two points of parallelogram as P and Q. Okay, and what the proof says is, we are going to write it in terms of symbols. What the proof says is, I'll write here to prove. Okay, to prove area of triangle ABC, okay, is equal to half the area of parallelogram, okay, P dot parallelogram ABQP. Okay, so I'm going to use highlighter. ABC, the area of this triangle, is half of this parallelogram. This is the parallelogram. Yes. So this is what we have to prove. Now let's see how we can prove this. Before we prove it, let's get rid of these highlighted things. Okay. Also, let's get rid of this. Oops. These things I don't want. Okay, fine. Now, before we start with the proof, we have to do a, let's do a small construction. What will be that construction? Now, focus on this line AC. Okay, this is one side of the triangle. Can we construct a line parallel to this AC? What I'm going to do is I'm going to construct a line parallel to this AC and with the same base AB. So, how I'm going to do that is something like this. Yes. Okay, it doesn't look that parallel, so let's maybe like this. Yeah, this is good enough. And I'm going to name this new point as equal to Z. So let's call this new point as Z. Okay, okay. So focus on this. I have constructed a new line BZ, which is parallel to the line AC. That's it. That's the simple first step that I'm going to do. So I'm going to make a note of it. Step number 1. So let's write it here. Step number 1. Construct a new line, okay, BZ parallel to the line, not line, it's in fact side, parallel to the side AC. Okay, so we have done that. Now Second point is going to be point number 2. So consider, okay, consider quadrilateral ABZC. Okay, I'm going to use a highlighter to highlight it. So AB, okay, and this is Z and this is C. Consider this quadrilateral ABZC. So in this quadrilateral, we have, okay, we have opposite sides, opposite sides parallel to each other. Opposite sides are parallel to each other. Yes, that's true. Why? Because AB is parallel to this CZ. That's how we started our proof. And then we have intentionally created BZ parallel to AC. So opposite sides of this quadrilateral are parallel to each other, and thus this is an important condition to prove that any quadrilateral will be a parallelogram. So we can very confidently say that this quadrilateral, okay, the quadrilateral that is highlighted here is a parallelogram. So let's zoom out and continue. Okay, thus, so this is my point number 3. Thus, ABZC is a valid parallelogram. Parallelogram. However, okay, in this parallelogram, we have this diagonal as BC. Okay, okay. So this is my diagonal BC. Okay, so we know that in any parallelogram, a diagonal divides the parallelogram into two equal parts. Okay, a diagonal divides a parallelogram into two equal parts. So this diagonal BC has divided this parallelogram into two equal parts. What are those two equal parts? One is our triangle ABC, the triangle which we are focused on, and another one is the triangle BZC. Okay, so I'm going to make a note of this point now. Here diagonal, okay, diagonal BC divides the parallelogram into two equal or congruent triangles. Okay, into two equal or congruent triangles. This is again another important property of a parallelogram. In fact, in the previous video we have proved this as a part of our theorem, that the diagonal of a parallelogram always divides it into two equal parts, and therefore area of triangle ABC is equal to area of triangle BZC, okay, and it is equal to what? It is half the area of parallelogram ABCZ. Okay, this is a very important statement. Now what I'm going to do is I'm going to take this figure down because I'm going to need it further. Copy, yes, and paste. Yeah, here it is. So note this important point, that area of triangle ABC is equal to area of triangle BCZ, which is equal to half, because the diagonal divides, here it is, the diagonal BC divides the parallelogram into two equal triangles. Okay, so area of triangle, so the point of focus for us is area of triangle ABC is half the area of triangle, area of parallelogram ABCZ. However, okay, now important point, point number 4. However, area of parallelogram ABCZ is equal to area of another parallelogram, which is ABQP. Okay, now I am going to use another highlighter. Okay, AB and QP, this is another parallelogram which is between the same parallel lines and having the same base AB. So we have just seen in the previous video that if there are two parallelograms which have the same height, which are on the same base and which are between the same parallel lines, then they will have equal area. Okay, this was the statement here. Let me read it out. Parallelograms on the same base and between the same parallels are equal in area. We have proved this in the previous video. So here we can see we have two parallelograms which satisfy this property. The one is highlighted in the green ABZC, and the other one in blue, ABQP. So parallelogram ABCZ will have the same area as parallelogram ABQP. Okay, and that's it. This is the point that we are going to substitute in this equation. So area of, because area of triangle ABC is already half the area of this parallelogram, but this parallelogram ABCZ is equal to parallelogram ABQP. Okay, and hence we can say that area of triangle ABC is equal to half the area of our original parallelogram, which was ABQP. Okay, and this is exactly what we wanted to prove in the beginning. Here it is. So we wanted to prove that area of triangle ABC is half the area of parallelogram ABQP. So ABQP. Okay, BZ did not exist. BZ is a line which we constructed in order to prove this theorem. So if I erase BZ, which is what I'm going to do now. Oops. So first, let's remove the highlighted things. Yeah. So as you can see, BZ is something which we constructed on our own. So let's try to erase that. Yes, and this didn't exist. So this was our original figure, and we wanted to prove that ABC, this triangle, is half the area of this parallelogram, and we have successfully proven that.